Hey guys, welcome to Confusing Bits. I'm Corey, and today we're going to be talking about Haskell programming from first principles. Look at all of that shiny stuff by Christopher Allen and Julie Moronuki. Pure functional programming without fear or frustration. If you're my normal watcher, I'm a programmer, and we're going to be talking about programming things, software development things. So if that's not your cup of tea, maybe skip this one. But I'll give you if you're planning on sticking around, the too long didn't read is that about the book. The book is really great. Introduction is a very thorough introduction to Haskell. I would highly recommend it, and Haskell in general. If you're looking to learn how to get into functional programming or learning more about real functional programming, you can do functional style programming in a lot of languages. I'm talking about pure, strongly typed functional programming, then yes, you definitely want to learn Haskell. And it's not super duper academic. You could program it, more or less as easily as any other language, but you just got to learn the syntax. It's just a weird syntax. You've forgotten you've forgotten how hard learning new syntax was. Yeah, I would recommend Haskell in general, but there's more nuance to that. So if you're interested, stick around. All right, so let's do the little thing on the back. Think learning Haskell is different. It doesn't have to be. Learning Haskell from the ground up is easier, works better for both experienced hackers and people who are new to programming. This book is designed to help you get to a place where you can begin applying Haskell to the everyday problems you want to solve. And then the blurb is, this is the best book on Haskell, any programming language I have ever read. Thank you so much. This Haskell book explains the complicated ideas in the most effective, simplest way that I have ever seen. In any programming book, you could only read one Haskell book, then read this Haskell book, and you will not be disappointed. I agree completely. As you can see, this is quite the mighty tome. This took me, because I was super duper, kept putting it off and on and off and on and off. It took me like 2 years to get through or something. It doesn't really take that long. If you sat down and just did the exercises like an hour or two every day, you probably get through it in like a month or two. But as you can see, it's how many pages is it? It is it's 1,000 pages. It's just over 1,000 pages. It's quite complete. So let me talk a little bit. We'll do that in a little bit. Okay, so there are a buttload of languages that you can learn, right? And just for reference speaking, I do kind of contract development work. So I work for different clients on a variety of different projects, oftentimes new field projects and web-based, and in the past mobile as well. Most of that development is with JavaScript or TypeScript. They're interchangeable to me. And often with React and React Native on the front end, and then on the back end it might be Node, it might be Java, it might be Python and .NET, C#. So I've used a bunch of different languages. Mainly, the main two languages that I use on a daily basis is JavaScript, TypeScript, or C#. And I'm fairly comfortable with that language. And one thing I've learned many different languages. I probably have decent experience with close to maybe half a dozen, maybe a dozen different languages, but they're all variations of the C style language, like your Pythons. And Python, if you take C, or you take C Sharp, or you take JavaScript, and you remove the squirrely braces under the hood, the execution model is the same. With Python, you just remove the little squirrely braces, and it's the same thing, right? It's not really doing anything useful. All of these languages, they're mutable. You could change values willy-nilly. There's no discipline about value manipulation. And it's mutable by default, nearly all of these languages. It's not like you opt into that mutability. You have to, just in the back of my mind, anytime you're working with one of these languages, you have to think, okay, this value could have changed or has changed at any given point along the program execution. So I have to read the whole program. I can't just think about the value as it is now. And also, they're all eager languages, meaning you go from one statement and that statement is evaluated then, at that particular time, unless you're just calling a particular function that is quote unquote lazy by design. I think like streams are lazy in like Java or something like that, because you have to get to the thing and then you do the evaluation. I guess another example would be C Sharp. I'm not super keen on the details of C Sharp, but you do the link queries or whatever, and then it's lazy-ish, like it's not evaluating you do the to list or whatever, or something like that. So there are some like lazy elements within a language, but generally speaking, once you leave that line goes to that assignment, whatever that expression gets evaluated, and then you move to the next expression, and then immediately it evaluates that next expression, and so on and so forth. You're going down the program. You just procedural execution model, eager procedural execution model. Most of the mainstream languages that we work with have that as a core way of thinking about the program, right? And of course, that comes from the C style, the C background, because C was basically a quote unquote portable assembly. So, and assembly is eager execution, right? So the point I'm getting at is most of the languages that you might want to learn. So if you're like a JavaScript developer, I want to learn Ruby. Ruby looks really neat. Well, you're not really going to learn a whole lot by learning Ruby. Same thing if you say, well, I'm going to learn PHP, or I want to learn Java, or I want to learn C Sharp. Well, I think maybe going from like JavaScript to like Java or C Sharp, you're going to learn, because you're going from a typed dynamic language to a typed language, a statically typed language. You're going to learn something there about types and stuff like that, but you do have to think about types in JavaScript. It's not something that you can't just avoid thinking about at all times, So, so that's. They're more, to me, in my mind, they're more similar than they're different. And so when I talk about when you want to learn a new language, oftentimes, first of all, you should if you just learn how to program or whatever, you learn the money-making language first, right? And generally speaking, that's going to be JavaScript. Maybe in your particular market, your local market, the only developer jobs that they're hiring for is C Sharp. If that's the case, then you learn C Sharp, right? Or maybe it's Java. Whatever language is in your local market, and you want to work in that local market, whatever market you want to get into, just learn whatever the de facto language is for that market. Get your programming, your first programming language, get your foot in the door, and then you can start exploring other languages. Don't be jumping around, right? Don't find the one that fits. No, you find the one that works, right? The one that's going to get you the job. Especially if you want to get a job as quickly as possible. Now, if you're in college and you got 4 years to waste, you're going to learn a bunch of different languages, because you're not going to be getting a job for a while. So maybe take that time. But anyway, I'm digressing. Hold on a second. So the whole point about that is talking about all of these different languages is to say most of the mainstream languages are all the same. Generally speaking, they're very similar. The relatively speaking relatively minor syntactic differences between the two. One of them might compile to native machine code and like C or C++. Others might need a virtual machine and a runtime like .NET or Java, and then other ones are interpreted dynamic languages like Java and Ruby. There are differences, significant differences between these, but they're more like than they are different from a programming language standpoint, not a technical implementation standpoint. So, but there are languages that are much different. For instance, Haskell is called an ML style language. That was the original successor of the language. There's also Lisp. Those are the ones with all of the little parentheses and stuff. You got a billion nested parentheses. There's also that's also another kind of functional program. That's kind of a dynamic. I've never done it before, so I'm kind of talking about what I know in general. But like if you go like Clojure or something like that, it's kind of a dynamic programming model, which is a different style of kind of functional programming. And then you also have some really more esoteric programs like APL, or is it Coq or something like that, where it's like this array-based languages or stack-based languages, which is a completely different kind of programming style. Those are the ones with the super duper terse, which is just a bunch of symbols. Like in one, like you have these one-liners that are like 12 characters long, like literally, and it's like doing a whole bunch of stuff. That's something. What was it? Code Report, I think, on YouTube loves APL. He has quite a few languages on like APL and similar style languages. And then what is the other type of language that I'm trying to think of it? I had it in the back of my mind and it completely blew my mind. But anyway, there are other programming languages that are nowhere near, like if you compare like C# to Python, you think there are huge differences, but you compare C# to APL and you're like, yeah, okay, I get your point, Corey, right? So that's what I'm talking about. So what is Haskell? Why would you learn Haskell specifically? Because there's a lot of functional programming language. So I'm going to list off a few. You might learn a language called Elm, which I do kind of recommend. Like if you're just kind of getting into functional programming, this will let you do statically typed functional programming, type safe. Like you get most of the benefits of going with a functional typed language on the front end, and there's also back end solutions as well, but it's mostly designed for the front end. You can do that as kind of an introduction to functional programming. I think it's a great introduction. Eventually, maybe at one point I'll do a review on this language and talk about Elm in general, but today we're going to talk about Haskell. You can also go, I said, the dynamic route like Clojure or some other type of Lisp or something like that, which I would love to get to eventually, but I already the core reasons why I wanted to learn functional programming. First of all, I heard about all of this category theory nonsense. I didn't really have any idea what they're talking about when they're talking about category theory or the lambda calculus or any of this stuff. And you don't directly need to know this stuff, but it's really helpful to know, and you will learn it in this book, what all of those things mean. And that was my keen interest. But the reason, but from a technical standpoint, why would I want to learn Haskell specifically? Well, you should know Haskell is a typed function, is a pure. That means they're extremely disciplined extremely disciplined about side effects. Side effects would be things like writing to a file, or talking to a database, or making a network request or something like that. In Haskell, all of that is managed, right? It's managed with a thing called an IO monad, which I won't get into, but all of your side effects are managed. You just state the side effect that you want, and the runtime handles the actual execution. You don't tell it to do this, do this, do this. When you're inside the IO monad, that's how you write it, but it's all in that one particular place. The rest of your code, if you're not inside the IO monad, you don't have to think about side effects at all, because it's all declarative function definitions. It's a very different way of programming. So it is pure. It's also a statically typed functional programming language, meaning you have types. So when you're typing things, you get good autocomplete because the language server actually knows what's available, and so you get those niceties as well. It's also you generally speaking, you at the edges of your program, you got to determine types, and the library is obviously determining types, but all the type inference is basically perfect. It's not like C# where there'll be these little edge cases where the type inference can't quite tell you. It should know that this thing is null or not null, but it doesn't know because they didn't code in that specific situation or something. Like, you run into that with TypeScript and C# all the time. But even though it has null safety, right? ML style language. Haskell uses a particular kind of I'm throwing out the name of it. It's used all the time. It uses a type evaluation system that it can completely evaluate your programming without, generally speaking, even defining a bunch of types, because you can define a function that is kind of generic over its input parameters, and you don't have to do the generics, the T's and the V's and the U's and the V's, and you don't have to do the generic programming. It is generic if you don't specify a type. You can unless you define a type constraint, you don't have to specify a type unless that function just happens to need to be constrained to a particular type. Anyway, so you've got polymorphism like right out of the box, just because the type system is so flexible, right? You can have a function that works on numbers, works on strings, works on tuples, works on sets, works on a wide variety of what would be overloaded functions in something like C or C or Java. C# or Java would be like overloaded functions, but it's all just one function in Haskell is what I'm getting at. Because you can do this kind of generic language. Also, because the type system is an algebraic type system, so you can define the type system is a lot more expressive. So in most programming languages, you really only have what are called product types. Product types would be like an object. An object has a number of fields, and each one of them can be independently different values. So you could think of a point. And a point has an X and a Y. That's a product type because X can be 3, it can be 5, it can be 10, it can be 10,000. And independently, Y can be 3 or 5 or 12 or negative 34. It's complete. Those two, the X and the Y, are completely independent. So it's X, the number of states that the point product type, which is why it's called a product type, is the X times the B's number of states. So it's an explosion of types. But you also have sum types. The most basic example of a sum type that you probably know of that you don't think of as a sum type is a bool, a boolean. It's either true or it's false. It's two different states, and now you add them together. What is? Do you see that? Why is it showing? What is that? Okay, this is some kind of weird Mac thing or something, where you do the peace sign and you get balloons. That is so weird. I don't know if you see this, but I'm seeing like balloons come up whenever I do that. That's so weird. I am flabbergasted. Maybe it's a thing for my webcam. That's so weird. I'm completely thrown. So okay, so you got sum types. And Boolean is a sum type. You have true or you have false, meaning you have true and then you have false. You add them together. There's two different states that a Boolean can be. It's true or false. That's why they're called sum types. So combine those two things together, and it's an algebraic type system. Along with usually once you have an algebraic type system, then you get like really nice pattern matching going along with it. So we're not going to get into pattern matching, but it's a more readable like switch statement, if you could think of it that way. Anyway, so that's another factor. So we got purity, and we got typed functional language, and of course functional languages mean there's no classes. It's not really classes in the traditional sense. It's just functions. Everything that you do is a function. You're gonna write a class, it's a function. If you're gonna write a factory, it's a function. If you're gonna write a repository, it's a function. All of these design patterns that you usually think of in other languages, it's all functions. It's functions all the way down. It's just like turtles all the way down. It's functions all the way down. So so that's Haskell. Also, another thing that makes Haskell interesting is it compiles down to a native executable, meaning once you compile it, you want to go deploy your program somewhere, you don't have to install a runtime or anything like that. There is no Haskell runtime that the user has to install. Just like if you want to run Java, you got to have a Java runtime. If you have C#, you need a C# runtime. If you want to run JavaScript on the back end, you need to install a JavaScript run. Same with Python. You have all these runtimes, right, for all of these VM languages, even interpreted virtual machine languages. Haskell's not that. It's going to produce a native executable. And it also, because it's pure and it's statically typed, it knows a whole lot more about your code, so it can be really efficient about the way it's compiling, also the way that it's executing programs. It's also I forgot what I was going to say. But so that's why you would want to learn Haskell. Mainly for me, it was mostly specifically because I was mostly happy working with Elm. I do think it's a nicer like beginner functional programming language to work with Elm, but I definitely wanted to learn because I kept hearing people all the time in the Elm community talking about how Elm doesn't have type classes or higher kind of types, and it doesn't. I didn't know what this monad thing was, and this functors and this applicatives and these transformers and all of this kind of jargon and stuff like that. So I wanted to know what that was, and the best way to know is to learn Haskell. Another thing about learning functional programming, because everything is immutable and because it's all pure and functional and stuff like that, things can be parallelized. So CPUs haven't been getting faster. Whenever I left the Marine Corps, it was early 2000s. The Pentium 4 had just come out, and I think I saw like overclocks at that time hitting 5 gigahertz on the CPU. We haven't gotten any faster. On the CPU cycles, we haven't really gotten any faster. Of course, the instructions per cycle, instructions per clock cycle have gotten more or less better. We've also got specialized functions the SEE and other stuff like that. So we have specialized functions on the CPU that speed things up. But the main thing that has happened is the caches have gotten bigger on the CPU die, meaning the memory. We've got more memory closer to the CPU, and we've got a lot more cores. Only problem with having more cores is that you need to program. For your program to be able to use more cores, it needs to be written in a manner that can use those cores. And your traditional languages are terrible at parallel and concurrent programming and stuff like that. I guess parallel is the right word. I always get all of those mixed up. But generally speaking, like JavaScript, there is practically speaking no parallelism. I mean, you could do some weird hacks with like web workers and stuff like that, but generally speaking, even like a node on the server, you're talking about one single thread. It could do some garbage collection and other things like that on like other threads, but the main thread of execution, you can't. There are obviously primitives that let you handle that, but generally speaking, it's single threaded, right? And most of the other languages are that way. They'll be single threaded by default. If you do like a map over a collection, it's not going to, even though in a pure languages you could do a map parallel, that's automatic optimization you could do in a language that was pure. You can't do that in like C# because mutability can happen, right? In the interim, you know, there's no discipline over mutation. If you ever heard about Rust and stuff like that, they had the borrow checker and stuff like that. That's all ways of constraining mutation, so it can parallelize things very easily and optimize things very easily. But you've got to have all that additional complexity you've got to fight the borrow checker, so to speak. In the Rust programming language, they have the term called fighting the borrow checker because you're trying to use mutation. If you didn't have any mutation, you wouldn't be fighting the borrow checker pretty much at all. So that's the thing. If you want to mutate values, then you're going to have to buy into this extra complexity. And all of these languages, these other languages, traditional earlier language, C#, JavaScript, and all that stuff, they have mutation by default. So it's not safe to do that automatic parallelization. So they don't do them, even though it would be extremely beneficial. But with Haskell, the compiler can just do that stuff like automatically. It's just part of its thing that it's just going to do that, right? It's also interesting. So we have all my point being, the CPUs aren't really getting faster. So we can no longer, as software developers, our programs are always getting more and more complex, are always getting more and more bloated. And in the past, we could rely on the CPUs getting faster, like doubling every 8 months or 16 months or whatever it is. We can't rely on that anymore. We actually have to write performant code. So that was another interesting point of going with Haskell, is that it does produce a native executable and it has this really fancy compiler that will let you do all of these fancy optimizations and stuff. By the way, this is, in case you can't tell, this is going to be a very long video. Because we're just talking about introducing Haskell. We haven't even really gotten talking to the book. But anyway, so that's why it's interesting to learn Haskell. Plus, you get the street cred, right? You learn, oh, I know Haskell. I'll program Haskell. Yeah. You get the street cred. You know, the thing is like if you learn, even just like get introduced to Haskell just a little bit, it demystifies things. And you're like, oh, okay, all right, that's not really that big of a brag, you know, because it's just a programming language, guys. It's got unfamiliar syntax, but it's still just a programming language. Another interesting aspect about Haskell that is even different from Elm. So Elm doesn't have some things in it that it doesn't have type classes, hierarchical types. which I cannot explain to you on this video. That's what this book is for. It also, this is an eager language, so it eagerly evaluates more or less everything that you write. It'll be eagerly evaluated in much the same way that like your regular program is. But Haskell is a lazy language, so that's also another unique thing that that it does is everything is lazy by default. Things will not be evaluated until it absolutely has to be evaluated. So I can create a list, an infinitely sized list, and then run some operations on that list, and only the values that I needed to run that evaluation will be evaluated. It will not evaluate the infinite list. It will just, so for instance, if I have created an infinite list and then I take the first 5 elements, it's only going to evaluate those 5 elements, and then it'll be done. It's not going to continue. So you can write things in a very clean way because things are lazy. You don't have to say, okay, well, I have to create a certain amount, and then I got to take this, and then if I need it more, I got to reallocate some more. And you could just write things kind of more or less pseudocode-ish, right? In ways you would write things in like pseudocode without handling error cases because everything's lazily evaluated. Only at the end of the statement, when if things have to be evaluated, will it be evaluated? The whole language is that way. And they bring that home, and we'll start talking with the book. The very first chapter is called All You Need is Lambda. And what that is it talks about the lambda calculus. And this chapter alone is reason to read this book because it really, for me, it was the big critical defining, and obviously it's probably why I put it in the first thing. It's the big defining aha moment for me whenever I read this chapter, because it talks about lambda calculus and then it says, okay, and the lambda calculus is you write out this like series of statements, and then you do like a simplification that like evaluates everything, and it says, okay, well, you've done all this operation, now you know how to do the calculations. Well, now you know how the execution model for Haskell. So you have all of these long expressions or whatever, and then you do a simplification, and then that's how programming is done in Haskell. That's how the evaluation, the semantics of how the lambda calculus is evaluated is the same as the way Haskell is, because it's based off the lambda calculus. And that was just mind-blowing for me, because it sounds fancy when I say lambda calculus, but go back to like 9th grade, 8th grade, or something like that. You're doing algebra 2 or algebra 1, and you got these equations, and they tell you to simplify the equation, right? They got a bunch of x's and y's and stuff like that, and it's really long, and then you can go through and you can multiply things and divide things, and you can simplify the equation down to 1. That is the same thing as the simplifying that I'm talking about, the evaluation in the lambda calculus. That is how execution happens. That was the thing that was mind-blowing to me, was that simplification, that thing that you did like in high school algebra. That is computation. And I'm never, for me, that was just mind-blowing when I thought about it. I was like, oh, you're right. Yeah, it totally is. That's an algorithm that you're doing when you're doing the simplification process. That is a runtime that you're running in your head. And that is the exact same way that Haskell works. You write all of these expressions, and your program is a big long statement at the end, because everything's pure and it's all unevaluated. Whenever on the language side, everything gets expressed in this very long, huge expression, and then the compiler gets asked, simplify this expression, and the compiler will simplify everything that it can simplify, and that's compilation. and then runtime will kick it off, and then it will simplify it the rest of the way. So that's, for me, that was mind blowing. Thinking about execution in that way, because that is not the model, the kind of C style model where it's do this, then do that, then do this, then do that. Because the sequence is very heavily ingrained in the C style model. Sequence is not heavily ingrained in a functional style programming. You're writing expressions. You're going to write a bunch of. It's getting closer to that idea of, here are a bunch of true statements that I'm just going to keep stating true statements until I have a provably correct series of statements that is consistent, and then that is my programming. It's not quite that level. There is another language that I'm also interested in that really drives that home, and that's like the fundamental concept is really being able to encode your programming not just as a series of expressions, but you can code your programming at the type level. Almost everything that you would normally you can express more at the type level. So that's iterative, and I think eventually that kind of stuff will make its way to Haskell. But that was the thing that blew my mind, was the simplification of expressions is the execution model for the programming, and that just blew my mind. That's like right out the gate. So there's that joke. I saw it somewhere else. I can't remember the exact joke, but there's two different ways that people teach programming. They either start with the theory, and then they move on to category theory. Or they either start with the lambda calculus and moved on to category theory. They start with category theory and they move on to lambda calculus. So, these are all like really, abstract concepts. Like the whole point, the joke is obviously to ruin the joke by explaining it, is that it's really heady stuff, right? But it doesn't have to be, and that's what this book is about. So let's just do the chapters just to give you an idea of everything that you're going to see. This by the time you get to this book, end of this book, you're going to have a base level of understanding of Haskell to be able to just write everyday programs. I'm sure there'll be a lot of fancier stuff that in the Haskell community that you don't understand, but you will be able to write your own programs using all of the idioms from the language. So you're gonna learn category theory along the way, or at least some pieces of category theory along the way. So I talked about the first chapter was about the lambda calculus, and then they do a kind of a they do a Hello Haskell thing. They talk about strings, and because there's a bunch of different string types in Haskell. It seems like anytime you get into a low-level language, you have to start thinking about string representation. So they talk about strings, and they talk about all the basic data types, and then they go on to about types and type inference. Then we go on to type classes. Type classes, I'll just say that they're like composable interfaces, so to speak. So they're kind of like interfaces that you can compose. Just you can implement. So you could define someone else can define a type class, and you could just implement it right on your classes wherever it is. And by the way, monad, functor, and everything—they're all type classes, right? So these category types are implemented as type classes in Haskell. And then there's more functional patterns. They talk about like what is point free style. So if you have a function that takes an A and then it has some type of let me see here. Yeah, okay. So you have a function that takes an A, and then it's equal to like taking the first element of a list and then the list. And so the A is the A's on both ends. Like in the equation simplification, if you got something on both sides of the equal sign, you can remove them. You could divide them away or whatever. Or if they're both added to both sides, you can get rid of both sides. That's point freestyle. So it talks about that. And you're going to see this a lot more things that goes on in Haskell or mathematical based. And I don't mean like really particularly fancy mathematics. You don't need to know like calculus or anything like that. We're talking about kind of algebraic kind of understanding of mathematics. Maybe, an algebraic understanding of mathematics. That's the level of math that we're really talking about. And of course, there's the category theory and stuff like that. Lambda calculus, that's more advanced, but it's still, if you know algebra, you're going to be able to muddle your way through it. But the big concept in the language is things adhere more to mathematical concepts than they do to just programming jargon. So that's why you get words like functor and monad and stuff, is because these are interfaces. These are provably mathematically rigorous interfaces instead of being just ad hoc. So like IEnumerable is just an ad hoc interface. The developer who developed it said, okay, it's going to have this function and this function and this function. Whereas for a monad, monad has a particular criteria that has to be met mathematically, and you have to be able to prove mathematically to be able to say something as a monad. Same thing with functor, same thing with the transformer or something. There are laws that define what all of these things are. Now the exact method name, is it bind or is it return or is it whatever the method name might be, vary a little bit different from these different languages, but the concept, the interface, the conceptual interface is the same, because a monad is a monad is a monad. Any language that implements a monad is going to have the same it's going to have the same functional interface, right? So anyway, and that comes from math. That's my whole point, is that it's not arbitrary. So Haskell really leans into that. Things that are not arbitrarily, that are not arbitrary, but things that are you can think of it as like Haskell's type classes were discovered, not invented, right? That kind of thing. I don't know if you really go that way, but that's the kind of thinking that you think of. Less arbitrary decisions and more by not having these arbitrary decisions, everything fits together, just like math fits together. We understand how to add things and divide things and multiply things, and we have all of these rules and all of these proofs and stuff that power all of this stuff. Well, the same thing can be said of all of these category theory types and stuff, is we know the relationship between all of these things. So anyway, that was more functional paragraph. It talks about recursion, a function that calls itself. Talks about list, folding list. Folding list, that's a reduction, right? That's you reduce. And it talks about algebraic data types. Yeah, we talked a little bit about that already. Signaling adversity. What is signaling adversity? I don't know what that is. Oh, this is talk about higher content types. And higher content types is like the abstract or the generic interface. So you put like a higher content type. So the kind of a type would be like star equals star. Star goes to star, and that's like a function that takes one input and has one output. And then if you have a function that takes two inputs and has one output, that would be star to star to star. That's the kind. And so it's like the very highest level of abstraction of an interface. It's like, what are the number of arguments? That we're not even talking about types. What are just the numbers of the arguments? That's the kind, so to speak. I'm probably butchering that explanation, but anyway, So that's kind, and it comes into play. I won't pretend like I particularly deeply understand that. There is a topic on building projects that talk about modules and all of that stuff. So yeah, Haskell has a module system like built in. This also talks about testing. And then we start getting into the category theory, talk about monoid and semigroup. Then they move on to functor, and then to applicative, and then on to monad. It talks about the monad laws and stuff like that. And it talks about how to use all of those things we just talked about. The chapter title is called Applying Structure, but it's talking about taking lists and folding them and getting out of values and then mapping over different things and reducing things and stuff like that. Your general day-to-day stuff. And then we start getting, we start diving more into some of the, and it's talking, the reason why it's talking about this is because these are just going to come up all throughout the code base. You're going to be looking at the whatever type definition that you're working with, some other type you're going to look at and say, oh, is this a monoid? If it's a monoid, then you go, okay, I have this, I can use this function on monoids, and so you could reuse code over and over and over again because it applies to these different type classes. There's also the foldable, traversable, and reader, and then they talk about a state monad, and then parser combinators, which it's great for parsers if the name doesn't their name doesn't give it away. And then it has some exercises on dealing with these different types called composing types. And then it talks about monad transformers. And then once you get to that up to that, then we start talking about non-strictness. This is the chapter on laziness in Haskell and stuff like that. And then I also talks about basic libraries, which kind of goes over some benchmarking, and then some other things that you might like maps, sets, sequence vectors, a bunch of different things. And then finally we get to the IO monad, which is how you actually do IO monads. If there's going to be one function that's implemented in a Haskell program, it's going to be at least an IO monad, so that you could actually get a console output, right, of your actual program. So talks about IO monad, and then it talks about things that go wrong. So it talks about how to throw and catch exceptions. So I had a lot of functional programming language. Well, quite a few programming languages eschew exceptions. They don't use exceptions because exceptions break control flow and stuff like that. But Haskell does actually have exceptions. One of the things that kind of peeved me whenever I first, I'm like, why? And you'll run into it very quickly because you go to get something out of a list, and you naively, because you're new, you will try to just manually index into the thing. And of course, if the thing doesn't exist, Haskell will throw an exception for a list. There are no, the base list or whatever is not exception safe. So it's kind of a gotcha. There are kind of few, it's not the smoothest language ever to work with. There's some rough edges. And that's one of them, is it like right out of the gate, you're having to deal with exceptions. You're like, what? Of course, the point is you're not supposed to do that. You're supposed to do it a different way, but you eventually learn. But the good thing that I have noticed in Haskell is, generally speaking, exceptions are exceptional. There are a few cases, like I mentioned. Spitting on my mic. Ugh. So there are some exceptions. To exceptions, but generally speaking, it's not like Java land or C# land where here's a case that I don't know what to do with. Let's just throw an exception. Like exception is a go-to statement. When you throw, you should read that as go-to. And if you wouldn't write a go-to statement, you probably shouldn't write a throw statement. Because there's a whole bunch of baggage that goes along with exceptions Like you got the whole stack trace that you got to carry around and all of that stuff. So yeah, probably. So that's one of the kind of pet peeves that I had. That there are exceptions, and there are, I think, some libraries. So there's like a standard library in Haskell. It's called Prelude. There are some alternate preludes, alternate standard libraries that you can use in Haskell. Haskell is a really flexible language. You can change out your standard library. You can turn on language features, like a whole bunch of advanced language features that aren't in the base language. So things get pretty wild, because that's another thing about Haskell. Haskell is first and foremost a research language, right? And it shows. There are some warts in it. But so anyway, the thing with the exceptions is there are alternate preludes that are safe, that kind of try to change these exceptions to things like in Elm. If you try to access a list, an element in a list, and the list doesn't exist, that access returns a maybe, and then you have to you have to handle the just or the nothing. You have to handle the empty case yourself. So, but it comes back as a value. The value is the maybe type. It doesn't just throw an exception like willy-nilly. You don't have to catch anything. It's always safe to just check for something. You'll just get a value back, because you always get a value back, and that value can be nothing, right? So you could do that kind of thing in Haskell as well. There's a maybe in Haskell. And that's how things are mostly handled, from what I can tell with Haskell. Most people just use algebraic type system instead of the exception. But I guess sometimes it comes up that you just need to throw. And then the last chapter is a final project, where they talk about like actually writing an application, a simple application. So that's the book. Geez, we're almost an hour in. So, would I recommend Haskell? Assuming that you have your moneymaker language, and that language is most likely a C-style language. Yeah, I would actually recommend that you learn Haskell, because it's going to. For the longest time, I did functional style programming in JavaScript. Now, I still do to a good extent, although I've been walking that back, trying to deal with allocation, performance impacts of allocations and immutability in JavaScript. So you got to deal with the language that you have, not the one that you want, right? But I do prefer the syntactic style of functional style JavaScript. And I try to practice it where I can. But it's not anything like once you go to a language like Haskell or Elm, and a real functional programming language, especially a typed functional, it's a night and day different. For me, this is the exact type of style of programming that I would prefer to do all the time. I feel the reason why I like Haskell so far is, and also Elm, is the safety. I am in constant fear when I program. This is not just a JavaScript hate or whatever. I'm like, it pays my paycheck. I am not a JavaScript hater. I think that every language has its huge warts. I'm always ragging on my fellow .NET developers at work that you don't have any legs to stand on. .NET is a huge, atrocious abomination. I mean, it is better than Java. That's not a really high bar. So I think a lot of the problems that you're going to run into in Java, JavaScript, you're going to run into in things like C#. You're going to have to deal with nulls. You have to deal with the type system that you can't quite express what you want without having to jump through a bunch of hoops, because you have to do everything in the OO paradigm. I mean, maybe the right language features could make that better, but the fact that everything has to be a class. I'm not hating on classes or anything. If it was easier to work with classes, that would be nicer. But I think it's probably adding a whole bunch of extra things. You really just want to define the shape of your data, and then you want to be able to define functions that work with those shapes, hopefully in a generic way. And that's what you get with Elm, and especially in the generic way, because this is the big difference. Elm doesn't really have generic. So if you and the way that comes into play, it doesn't have type classes. So because you don't have type classes, you don't have interfaces, and so you don't have quite the level of code reuse. So Elm, whenever you use a dictionary and you call map on the dictionary, that is a different function than whenever you call map on a list, or if you call map on an array or on a set. All of those will be different map implementations. They'll be doing the same thing, but they'll be different implementations. With Haskell, you will implement the type class for monad, for list, or your own data type, and that will just be the one implementation. And you call map, the runtime's going to know to use the type class. So when you call map, it's going to say, okay, well this is map is implemented, but is part of the functor interface, or whatever it was. I can't remember the names of things. It's a part of the functor interface. So does this type does it have an implementation for functor? Oh, indeed it does. So we'll use that implementation. That's the kind of polymorphic dispatch, or whatever. I don't know the fancy words for things. This is where the types change, but the functions stay the same, right? So you don't have to implement things over and over and over again. You could just you can use these standard interfaces. There's going to be monads and functors and applicatives and stuff. And you just implement it. And a lot of times, if you implement it the highest form of, like, if you can implement a monad transformer, well, you're going to get like a bajillion different type classes for free. You're going to get like monoid and functor and monad and, of course, transformer. You can get all of those for free just because you were able to implement monad transformer or something like that. Now, I could be messing up the terminology, but that, you get me the gist, is that there are higher forms that other lower forms can just be automatically derived, and that's a thing that you could do. So on your types, if you want to like print something to the screen, in C#, you got to implement the two. If you implement a class, you got to implement the toString. If you want to compare two classes, you got to implement equals. Well, there's a similar thing in Haskell, but in Haskell, you could just do deriving, show, and equal, and it's just automatic implementation, because it knows enough about your types. It knows that, oh, I know how to compare the strings, I know how to compare the ints, I know how to compare the bools, so we'll just do all of that automatically as a default implementation. And so it's literally you write your type, and then you write deriving, show, which gives you your print, and then you write EQ, which is equal, unless you do equality checks. It just saves so much code. Like, there is a library, I don't know if it's in C#, but I know there's a library in Java that does, I think they have, like, you add a decorator to the class or something, and it's a library, and it adds that boilerplate for you. It'll add the toString and equals and a couple other ones, the hash or something. It'll write an automatic implementation for you, generate it for you. I don't think they have anything like that in C#. But anyway, that's the analog. But you don't have to reach for a special library. You don't have to have special syntax for it. I mean, you don't have to do anything special for it. It's just in the language. You just do deriving. If you've seen it in Rust, Rust has a deriving macros. Same thing. That's where they get it from. Rust was inspired by OCaml. OCaml, the OCaml ML, is an ML language. Haskell is an ML language. All the roots there. So if you're interested in Rust is like an ML and C clothing kind of. It's an ML that takes that allows that gets really disciplined about mutability. Let's put it that way. That's its core defining feature, and it's no cost abstractions. But anyway, I forgot where we got in here. I don't know what it is. So we're over an hour long, and I don't know if you're still watching, but so I think it's very valuable to learn a language like Haskell. I feel that this just gets back to it. I feel safe in a language like Elm or Haskell because the type system is actually dependable. If it compiles, there's a very good chance that I got it right. Now maybe I messed up the domain log, but it's not going to blow up. It's not going to throw an exception on me generally. It's generally going to work, and because the type system is so powerful, I'm also able to code a lot of the business logic in the type system. Just like if you're in a dynamic language, then you have to do checks for, is this a string? Is this a number? Is this a bool? You have to do those manual checks. But if you go to a type language, no longer you have to do those. You don't have to do those runtime checks. You could say, okay, well, this is a bool, and it's just a bool. There will always be a bool. You can always assume that this thing is a bool or a string or whatever type that you defined it as. But if you take that analogy and make it even better, what if you could start encoding your business logic in the type system? So you could have things, you could define, like if you wanted to define a I guess a good example is you wanted to define, if you wanted to declare a deck of cards in code, well, you could say that the face and the suite, and then the face is either the was it the diamond, the heart, and then the whatever, you get what I'm saying. And then the suite is the diamond, the heart, and the face is like the jack, the kings, the queens, and then the 10 through 1 and the ace and stuff like that. That's a sum type, right? Well, no, that's a product type. You put it's a product type, because each one of those could be individually. You need every permutation, so it's the suite times the face or whatever it is, and that's how you get 52 cards. So you could define that at the type level as literally those things. It's literally just the name of those things. So your type would be, this is a king, this is a queen, this is a jack, this is an ace, this is a 10, this is a 11, and so on and so forth. And then you have your diamonds, your hearts, and everything. You define all of those types, and then you make them a product and turn that into a card. And so now it's impossible to even represent an invalid card state. You have to construct one from any of those values. Those are the only values that you get. If that example seems weird or whatever, look. I guess the best is look up Steve Waluchin. Maybe one of the titles would be F# for C# programmers, or railroad oriented programming. Those are talks by that guy. He does fantastic. He uses that example, the deck of cards. He uses that example of having a deck of cards represented at the type level. And this is versus, like, if you did that in C#, you could do it with a nums, but it's not, and you don't have the you could do it with the nums, but it's kind of hacky. You could maybe try to do it with a bunch of different classes, so you could do polymorphic switching and stuff like that. They do that in Flutter. They have your like data loading states and stuff like that. They'll define it as a bunch of subclasses of such. So you can have like a I don't know, you have your different states of a request. So your request might be download users, and you have your users type, and the user can have a subtype that it's either not requested, and then it's loading, and then either successfully loaded or error loading, and that would be your 4 subclasses of your user data thing. And then you could switch off of that. They have pattern matching. So that's in Flutter. So but that's an OO style programming. That's how you have to do it in that one. You have to use subclasses. You have to use inheritance to do that. Anyway, so there are ways to do it. I'm not saying that you can't do this kind of stuff in other programs. I'm saying it makes it easy to program your. It makes it easier to program your business logic in a way that invalid states are not even representable in your type system, right? So you can't even write the wrong code. This really goes into that, this Idris or whatever. I haven't got into it, but this expands on that topic. It adds a lot of the algebraic data type system along with enumeration. So you could say you can have none of a thing, you have one of a thing, or you can have many of a thing. So you're able to enumerate things, and so that adds another level of way of expressiveness at the type level. So you could say I have exactly one user. And there's one user, and once you use that user, you have none users. And so you have to handle all of those cases and stuff like that. So it's handling enumeration at the type level as well, which is something is not generally available. It's called dependent types or linear types, so it could be more exactly. But this that's called linear types, I think. But the general concept of this higher level of expressibility at the type level is called dependent types, I believe. It's types that you can program. Types as parameters. So if you could take a type as a parameter itself, that is dependent type. So if you could just take a user class as an input to a function. Not this parameter is a user, but the user type itself as a parameter to a function. We're kicking up the level of abstraction. So that's what this is about. But that's getting into the type level. That's why I like Haskell, is that I feel I am always scared. I am the super timid programmer. I don't go more than like a minute or two. When I'm working on something, I don't go more than a minute or two without running the program, because I never know when I've mistyped something or whatever, and I'm not getting feedback from the LSP for whatever reason. Something misspelled. Maybe it was a string, because those are all over the place, where some string value that's typed wrong and you have to get the name right. There's no type checking for strings, and so I've just been conditioned over the years with JavaScript and C# to write a little bit of code and either run the test or run the program like over and over and over and over again. But with a thing like Haskell or Elm, I can go an hour and I'll just have the compiler running and it'll be telling me things that I'm erroring with, and then I fix all the type errors and suddenly my program works. It's really, for me, that's the way. I do want the compiler to go through and check everything for me. And I don't mind having to write a little bit extra code if it's making me handle all the cases that I didn't think about. I want the compiler to be going, okay, well, you handled all these cases, but you forgot about this case. How do you want to handle that? I would like my compiler to say, well, you didn't handle all the cases. Here's the case that you didn't handle. What do you want to do for this case? And the code is there. The compiler can know, with the right programming language, the compiler can know a lot more about what you're trying to do, and that's what you get with Haskell and Elm. I just love it, and I don't know that it's more productive. I just know that I feel better about my code. I know that's that's terrible. I'm supposed to be saying, well, it lets you, the strong type safety lets you write better code. It'll be less bugs, it'll have less bugs, and you can also do it faster. I don't know that. I really don't know that because I'm such a beginner. I mean, I've been programming JavaScript forever. I am not anywhere near as fast with Haskell, but I feel better with Haskell. I feel safer with Haskell. I feel more confident with Haskell. I would be more willing to deploy code quicker with Haskell. That's how I feel, but I don't know it, right? I don't know it to be true. And no one does, as far as I can tell. No one does. There are like some small scale there's some small scale research papers and stuff, but anytime you have research dealing with humans, especially complex, you're going to do a research paper and they have you implement programs in like a dozen different languages, and they want to check the number of bugs that were implemented and stuff. That's just so hard. Like, how do you make sure that all of these different developers have the same level of experience with that programming language? Skill in general, how do you control for that? How do you a complex enough program? How do you get a complex enough program? Because most of the problems that we run into is not codes that is not programs that are a few thousand lines of code. We're talking about tens, even hundreds of thousands of lines of code. That's where the problems come from. And what is, that's, you're in a different regime, and you're not going to get a research paper that has equal skilled developers that are equally skilled with their own individual programming language, all implementing 100,000 line equivalent solutions to a problem. You're not going to get an apples to apples. This is you can't make that comparison. And then you're also going to do it with enough samples, so you have like 100 of each developer for you to be able to say something realistic for each programming language. So you got 10 languages and 100 developers each. 10 developers, 10 languages, 100 developers. So you're 1,000 developers, and they make $100,000 a year. So what was it, $100,000 to $10,000? So it's $1 million. Just and that's all they're going to do for the next year to do this non-trivial project. That's all they're going to work on is this code base, right? For each one of the respective languages. You're not going to get that. You're not going to get that's the level of rigor that you need to get that answer, and you're just not going to get that answer. And I've seen where they do comparisons of like GitHub issues and stuff, and they're doing statistical analysis on bug reports for public repos for different programming languages and stuff like that, and you're just not going to get a good result from that kind of data. Anyway, I am rambling. I do recommend this book. I should offer an author. There is, if you don't want to get this book, there is another book. I can't state to the quality, but there was two main resources that people recommended to me whenever I was first looking into program. There was the Haskell book. Anytime if you start reading online about what book you should use to learn Haskell, what resource you should use to learn how, they're going to say the Haskell book. This is the Haskell book. The purple book is the Haskell book. There is another resource called Learn You a Haskell for Great Good. Or something to that effect. That's an interesting name, but that's also one that's highly recommended. I have looked at it, but I haven't gone through the whole material and stuff like that, so I can't state to the quality. I can't give an apples to apple comparison, but those are the highly recommend. And Learning Haskell for Great Good, I believe, is free. and it's online. So if you're cheap, you're a student or whatever, and you're wanting to learn Haskell on your own, that would probably be the option that I would go. Although this wasn't expensive, super expensive. I think it was maybe $50. How much? I don't know. I don't know how much it was. But you can get the PDF version. There's a PDF version, or I got the... I don't even know if these are still in print. This was... I had to do like a pre-order for this book to get the printing, because I think he did like an on-demand printing of these books, and that came with... I got this book and the physical book and another PDF version, because I'd already bought a PDF version. But I got them both together as part of the pre-order. So I actually have a spare PDF that I could probably give out, but I don't know. If you're interested, just message me. I will post, if I do give it out, I will post a pinned comment down below that someone's already got it. I can only have one free to give out. So anyway, I'm sure you can find it online. It's just a PDF, right? But I would recommend paying. This is excellent material. Definitely worth paying for, and I'm glad I bought it. I will, going forward. So I still like working with Elm. I still like working with Haskell. Haskell is probably going to be my go-to kind of server-side scripting kind of stuff, and problems, like if I'm just running problems on lead code, just trying to keep myself sharp or something like that, I'll do it in Haskell or something like that. If I'm doing admin code, I'm going to be doing it in Haskell, just because the standard library and the composability, and you reuse everything over and over again. It's just it's a very nice language. If you like Python, this is probably something I probably should have led with. If you like Python for its easy expressibility, and it's easy to write, it's great standard library and stuff like that, well, you can get Haskell and get 100 times the performance. So, and your machine learning workloads, you better believe Haskell has got some machine learning functions that'll probably perform like a bajillion. Your NumPy, this is math, okay? You're not telling me that NumPy is going to beat out something that Haskell's can do. This is not going to work. It's not going to happen. So anyway, yeah, this is a research language, so yeah, it's going to beat out Python every day of the week, in my opinion. I may be some expert in Python, machine learning, and data science, and people, they'll tell me otherwise, but if you're programming inside the IO monad, it's like an imperative language. You like do this. That's what the IO monad does, is it lets you sequence these. You do this, then do this, then do this, then do this, then do this. And it's, as long as you're programming in the IO monad, it's the best. What was it? Simon Peyton Jones, one of the authors, or the head of the Haskell language or whatever, he says like inside Haskell is the best imperative programming language ever, or something like that. So, but yeah, so I love it. I might not stick to. I am very glad to learn it, but I definitely want to get a little bit more into this dependent type stuff eventually with integers. But after that, I might move to something like, because I don't see myself making a career with Haskell. So this is just purely for my own intellectual benefit. I don't see myself convincing any coworkers or anybody that I'm working with to use Haskell. It's just not. I can't even Elm. I don't see myself getting. I don't see myself being able to make that sell, especially in the contracting space that I work. And because when I'm gone, someone else needs to be able to pick up the torch, and I can't just leave them with Haskell to maintain or Elm. Although I think it would be great it's going to be a hard sell, right? But another language that I think that could is Rust, because Rust has the bones of ML, and it has its enums in Rust are something like the algebraic. It allows it has pattern matching, and its enums are kind of like the algebraic data types. So you're able to have that level of expressivity. But you also compile down to extremely performant machine code. So that could be a next step for me if I was wanting another primary language, if I decided that was the next priority. The other thing is learning a language like APL or Lisp or Erlang. I think that's the other one. I wanted to learn something like Erlang. That seems really interesting. But that was the other language style that I was saying. I think Erlang's a dynamic language, I think. Anyway, looks interesting. But the whole point is we didn't talk. Let me give out the last little bit. When I first started learning Haskell, it was a pain in the butt. I would go to install the tools, and then I would get some weird cryptic like errors, like GHC, which is the compiler, would blow up and it wouldn't work. And then I would be working with Visual Studio and I try to install the plugin for Haskell to get the language server running, and then that would blow up. And there's still some paper cuts. Even I guess a couple of months ago, I was rebooting my Haskell project. I was just going to do some exercises in Haskell, and I went to get everything up and running, and then it says, "Oh, okay, we got a new version of the plugin, the Haskell language server plugin. We need to install a new version of VAC." So it goes and installs all that stuff, and then the language server, it's all the new GHC. The GHC got updated, and then whenever it goes to install the language server, it craps the bed because there's no coordination. There are two different independent projects. The compiler project does not coordinate with the language server project. So you can get a new compiler out, and then the language server can't talk to the compiler, which is, it's maddening. The tooling in Haskell, although it's far better than something like C++ or C or something like that, it's not even on the level of something like, I think, Java or C#. And that's not high praise, right? For me, a modern language ecosystem, you need to have one tool that does everything. Rust is a great example. You do Rust up, and that installs whatever version of Rust that's like your Rust version manager, and it installs whatever version of Rust that you want to have on your system. And then from everything else, all the commands are cargo. If you want to run test, cargo test. If you want to run if you want to build, use cargo build. If you want to run if you want what is all the tools? If you want to install a package, just do cargo add the package or whatever. If you want to init a project, cargo init. You have one tool to rule them all, and that's the way a modern language needs to work. Haskell is more akin, I guess the closest analogy would be JavaScript, where you can, yes, when everything's working right, it's a mostly fine experience, but there's all this disjointed tools and everything. You got this tool for that, this tool for that. There's one main tool called Cabal, and then for whatever reason they had this other thing called Stack that uses Cabal and like manages the dependency for Cabals, and if you muck around with Cabal, you can break the stack, and you have all these different tools. What Haskell needs it's just one hole. You need to have like GHC init, GHC run, GHC install package, GHC REPL, GHC. You just need to have one CLI tool to rule it all, and it's not there. And that's the biggest thing is this lack of coordination, lack of consolidation that has really made. I'm like, even in .NET, they now have the .NET CLI tool. You can do everything with the .NET, and if you need to do tools that are built off of the .NET tools, you can do .NET tools and then install the tool. So you can have tools that are installed with .NET tool, with the .NET tool. And that's the way you should handle it. That is the proper way to handle it. Have one single way to do the thing. And Haskell's not there yet. A lot of languages aren't, but that is definitely a pain point, especially. And another thing is there's definitely a neglect of Windows. That's where most of my frustration came with working with Haskell, was trying to run it on Windows. Eventually, I moved it over to the WSL on Windows, and things got a lot better. But eventually, I moved over to the Mac, and then that was working fine for a good long while. And then I got an M1 Mac, and then we were back in trouble again. So, I mean, this is tech. Got to remember, this is first and foremost a research programming language. The people who are working on this language, generally speaking, are not trying to make it a productive language. They're trying to get their next paper written, right? So there have been efforts of big efforts. Like when I guess 2 years ago, 2 or 3 years ago, when I first started really learning Haskell, the tooling was terrible. Now it mostly works. There is that occasional time where you'll go to install it, and then the language server isn't built yet for the new compiler, and so you run into language server errors. That happens occasionally, but it's not like every day there's a new compiler version. So I'm hoping eventually they'll work out these bugs and get some coordination and stuff, but it has gotten a lot better, and it has definitely been a focus. They have, for the last couple of years, I've seen them, like in the community, they've been doing these big high profile projects, community projects to improve the tooling for Haskell. So it is slowly becoming, I would say, a language with modern tooling, but it's not quite there yet. So that is also a kind of caveat. I probably should have led that not an hour and a half in, but yeah. This is just a contrast, like Elm. Elm has also basically one tool. I mean, there are some tools. It doesn't do formatting, and tests are not built in, but you basically just use Elm format, and then if you want to do tests, you use Elm test. And that's just, the community has decided that that's just what everybody's going to use, and the community has decided we're better off just making this one tool better than 20 different tools, like JavaScript. Like how many different, Vite and Parcel and Webpack and Bun now, and it's just so many. I keep walking away from the mic, so I hope you guys found this useful. I wish I could get my thoughts. I kept putting off this video for forever because I couldn't get my thoughts all in one place. It's such a big topic, and I knew I didn't want to go into the tutorial. You can get a tutorial about Haskell or whatever, but I want to have a larger discussion. By discussion, me talking at you. I want to have a larger discussion about the book, especially, and Haskell in general, and in general, kind of how I at least think long languages, learning a new language should be thought about. Thinking about the CPU performance and stuff like that, and functional programming versus C-style languages all being the same, and that kind of thing. Anyway, I'm rambling here, but I had so much that I wanted to talk about, and I wasn't sure that I could make a more pointed video. So if you stuck around, thank you. I hope it was helpful, and I'll catch you guys on the next one.